Microsoft is making bold moves in the race to build a truly powerful quantum computer, and their secret weapon might just be a bizarre particle called the Majorana Zero Mode. For years, they've pursued a radical idea: topological qubits. Unlike other types of qubits that are incredibly fragile, these Majorana-based qubits are designed to be inherently much more stable and resistant to errors, the biggest hurdle in quantum computing. And recently, Microsoft announced a significant breakthrough. They've demonstrated crucial progress in creating and controlling these elusive Majorana quasi-particles on a physical device. This isn't a chip you can buy yet, but it's a vital step towards proving their unique approach can work. If they succeed in building scalable, fault-tolerant quantum computers using these Majorana qubits, it could revolutionize fields like materials, science, drug discovery, and complex simulations. It's still early days, but this progress is a tantalizing glimpse into a future powered by truly robust quantum computation. Microsoft is betting big, and the quantum world is watching closely. The universe keeps surprising us, and NASA's James Webb Space Telescope is leading the charge. One of its most intriguing recent finds takes us to a distant exoplanet, K2-18b, roughly 120 light-years away. This isn't just any exoplanet. K2-18b is a Hyson world candidate, meaning it could have a water ocean beneath a hydrogen-rich atmosphere, making it a prime target in the search for habitable environments. Using its powerful infrared capabilities, Webb peered into K2-18b's atmosphere. It confirmed the presence of carbon-bearing molecules like methane and carbon dioxide, common in such atmospheres. But the real headline grabber was the possible detection of a molecule called dimethyl sulfide, or DMS. Why is this so exciting? On Earth, the vast majority of DMS in our atmosphere is produced by life, particularly marine phytoplankton. Now, this isn't definitive proof of alien life on K2-18b, far from it. The DMS detection needs further confirmation, and scientists are still exploring if non-biological processes could produce it on such a planet. But finding it, even tentatively, in the atmosphere of a potentially water-covered world is a tantalizing clue. It dramatically elevates K2-18b as a high-priority target for future observations, inching us closer to understanding if life could exist beyond Earth. Imagine an AI that doesn't just write code, but actually invents brand new, more efficient ways for computers to solve problems. That's the exciting reality behind AlphaEvolve, a groundbreaking new agent from Google DeepMind. So how does it work? AlphaEvolve cleverly combines the power of evolutionary algorithms, think survival of the fittest for computer programs, with the sophisticated understanding of Google's advanced AI, Gemini. It starts with a population of existing algorithms. Then, instead of relying on random changes, Gemini acts as an intelligent mutator. It analyzes the best-performing algorithms and uses its deep knowledge of code to creatively modify and combine them, aiming to generate even better versions. This cycle of evaluation, selection, and Gemini-powered innovation repeats, pushing the boundaries with each new generation of algorithms. And the results are already speaking volumes. When AlphaEvolve tackled the fundamental problem of sorting data, it didn't just rediscover known efficient methods. It actually designed entirely new sorting algorithms that, in specific scenarios like sorting smaller arrays, can outperform the highly optimized algorithms meticulously crafted by human experts over decades. It's like having an AI partner that can see new paths to efficiency. Building on the legacy of projects like AlphaDev, AlphaEvolve represents a significant leap. It's not just about one type of problem. Its framework has the potential to accelerate algorithmic discovery across a vast range of fields, from scientific computing to optimizing complex systems. Ultimately, AlphaEvolve is paving the way for AI to become a true collaborator in scientific and algorithmic discovery, helping us unlock new levels of computational power and ingenuity. It's a glimpse into a future where AI helps us design the very tools that drive progress. For decades, the black hole information paradox has haunted physics. What happens to the intricate details of everything a black hole swallows when it eventually evaporates? Does information truly vanish, tearing up the rulebook of quantum mechanics? Theoretical physicist Don Page offered a crucial clue, a theoretical lifeline, known as the Page curve. Imagine a black hole slowly radiating its mass away as Hawking radiation. Page predicted that initially, the entanglement entropy of this radiation, a measure of its quantum messiness, or how much information it's missing from our perspective, would steadily rise. This makes sense. The radiation is deeply entangled with the shrinking black hole. More radiation means more missing information. But here's the vital twist. Page argued that after the black hole evaporates past its halfway point, the critical Page time, this entropy must start to decrease, eventually returning to zero as the black hole vanishes. This would mean the radiation is becoming purer, and the supposedly lost information is somehow being encoded within it and carried away. For years, exactly how this decrease occurred remained a profound, seemingly impossible puzzle. Then, a stunning revelation emerged from the complex mathematics of quantum gravity. Scientists discovered that at these late times, a region inside the black hole, a portion of its interior dubbed an island, becomes quantum mechanically entangled with the radiation that has already escaped far away. The information content of this island effectively becomes part of the radiation system we're observing. When calculations meticulously include this island, the entropy of the radiation beautifully follows the predicted Page curve. It rises, and then it falls. It's as if the information, once thought trapped, finds a quantum pathway out, encoded in subtle, intricate correlations within the complete history of the Hawking radiation. So the Page curve, once a theoretical prediction, now, thanks to concepts like these, quote, islands, provides powerful evidence that information is indeed preserved. Quantum mechanics seems to hold firm, even at the enigmatic edge of a black hole. Imagine this. Late December 2024, and a new near-Earth asteroid, designated 2024 YR4, is discovered by NASA-funded telescopes. Initial calculations paint a concerning, though small, possibility, a potential Earth impact on December 22, 2032. This asteroid, estimated to be the size of a 15-story building, was large enough to cause localized damage. Because its initial impact probability crossed a critical 1% threshold, alerts were formally issued to government agencies and international planetary defense groups. The world was watching, but science is a process. As astronomers gathered more observations through early 2025, the picture sharpened. By March 2025, even NASA's powerful James Webb Space Telescope had weighed in, refining 2024 YR4's size to between 170 and 220 feet. And with this new data came relief. Experts at NASA definitively concluded that asteroid 2024 YR4 poses no significant impact risk to Earth in 2032 or any time thereafter. So, while a direct hit was ruled out, 2024 YR4 served as a vital real-world, or in this NASA scenario, a realistic exercise, test of our planetary defense systems, from discovery and tracking to risk assessment and international communication. It reminds us that while the cosmos holds potential hazards, ongoing vigilance and scientific collaboration are our best defenses. And though there's a tiny chance it might graze the moon in 2032, our planet is safe from 2024 YR4. The quest for true quantum computational power took another leap forward recently, with Google's quantum team once again pushing the boundaries. They unveiled a powerful demonstration using their upgraded Sycamore quantum processor, now boasting around 70 operational qubits. So, what did they achieve? The task was something called random circuit sampling. Essentially, running a complex, randomly chosen sequence of quantum operations, and then measuring the outcomes. Think of it as a highly intricate quantum stress test. Here's where it gets mind-bending. Google's Sycamore processor crunched through this incredibly complex task in a matter of seconds. Now compare that to the estimated time for even the world's most powerful classical supercomputer at the time, Frontier, to achieve the same result, an astonishing 47 years. This isn't just about being slightly faster, it's about entering a regime that Google terms beyond classical computation. It signifies immense progress in building larger, more capable quantum machines and serves as a powerful benchmark, proving these devices can perform tasks that are, for all practical purposes, impossible for our current best conventional computers. Now, it's crucial to remember this specific task isn't directly solving a real-world problem like discovering new medicines yet. It's a carefully chosen benchmark. The journey towards fault-tolerant quantum computers, the holy grail that can tackle such grand challenges reliably, is still long and complex, requiring robust error correction. But each step like this, each demonstration of quantum hardware outperforming classical systems on specific tasks, is a vital signpost. It validates the underlying physics, showcases technological advancement, and inches us closer to eventually harnessing the strange and powerful rules of the quantum world to revolutionize science and technology. Imagine ripples in the very fabric of space-time, cosmic whispers predicted by Albert Einstein a century ago. For decades, these gravitational waves remained theoretical, their signals deemed almost impossibly faint to detect. But human ingenuity rose to the challenge with LIGO, the Laser Interferometer Gravitational Wave Observatory. These colossal L-shaped instruments, with arms stretching kilometers long, are marvels of precision. Lasers race down these vacuum-sealed tunnels, bouncing off perfectly polished mirrors. When a gravitational wave from a cataclysmic event passes through Earth, it subtly stretches one arm and squeezes the other by an amount far smaller than the width of a single proton. LIGO's incredibly sensitive detectors can pick up this infinitesimal dance. Then, in 2015, history was made. LIGO detected the unmistakable chirp of two massive black holes, each about 30 times the mass of our Sun, spiraling into a cataclysmic merger over 1 billion light-years away. This was humanity's first direct observation of gravitational waves, opening an entirely new window on the universe, a way to hear the cosmos, not just see it. And the discoveries didn't stop. In 2017, LIGO, alongside its European counterpart Virgo, captured the gravitational waves from two neutron stars colliding. This time, telescopes around the world also saw the light from the explosion, from gamma rays to radio waves, heralding the era of multi-messenger astronomy. This landmark event even confirmed that gravitational waves travel at the speed of light. LIGO isn't just confirming Einstein, it's allowing us to probe the universe's most extreme phenomena, from the hearts of black hole collisions to the exotic matter inside neutron stars, giving us an entirely new sense to explore the cosmos. What if the force accelerating the expansion of our universe isn't constant, but is actually changing over time? New results from the Dark Energy Spectroscopic Instrument, or DESI, are giving scientists intriguing new hints that this might just be the case. DESI is on a monumental mission to create the largest 3D map of the cosmos ever assembled, charting the positions of tens of millions of galaxies and quasars across 11 billion years of cosmic history. By precisely measuring how the universe has expanded, DESI is probing the very nature of dark energy, that mysterious something that makes up nearly 70% of our universe and is pushing everything apart faster and faster. Now, based on its first year of incredibly precise data, DESI's findings are largely consistent with our standard model, where dark energy is a constant. But there are tantalizing discrepancies. When combined with other cosmic observations, the DESI data slightly favors a picture where dark energy evolves, its strength perhaps varying as the universe ages. This isn't definitive proof yet. The evidence is suggestive, not conclusive. But if these hints are confirmed as DESI collects more data over its 5-year survey, it would revolutionize our understanding of cosmology. It could mean new fundamental physics, a different ultimate fate for our universe, and a deeper insight into one of science's greatest mysteries. The universe, it seems, may still have some big surprises in store. Born from the fiery death of massive stars, neutron stars are cosmic wonders. Imagine crushing 1.5 times the mass of our Sun into a sphere just 10 to 20 kilometers across, the size of a city. A single teaspoon of this ultra-dense matter would weigh billions of tons on Earth. This incredible density forms when a star's core collapses in a supernova, forcing protons and electrons into a sea of tightly packed neutrons. But the extremes don't stop there. As the core collapses, it spins phenomenally fast, sometimes hundreds of times per second. If its powerful magnetic fields are aligned just right, these spinning giants sweep beams of radiation across space. When these beams pulse towards Earth, we see them as pulsars, precise cosmic lighthouses. Then there are magnetars, a special kind of neutron star boasting the most powerful magnetic fields in the universe, trillions of times stronger than Earth's. These fields are so intense, they can cause starquakes on the star's surface, unleashing colossal bursts of energy. Unlike a black hole, a neutron star has an incredibly exotic, solid crust. And when two of these dense remnants collide, they create a spectacular kilonova explosion, forging many of the heavy elements in the universe, like gold and platinum. Neutron stars truly are laboratories for extreme physics. Quantum mechanics describes a world of probabilities, where particles can exist in multiple states at once. But how does this fuzzy quantum realm give rise to the definite reality we experience? The many worlds interpretation offers a truly radical answer. Proposed by Hugh Everett, this theory says that whenever a quantum event forces a choice, like a particle being here or there, the universe doesn't pick one outcome. Instead, the universe itself splits, or branches, into multiple parallel universes. In one world, the particle is here. In another, completely separate world, it's there. And you, the observer, also split. There's a version of you in each world, each experiencing a different outcome as their reality. There's no mysterious collapse of possibilities. All possibilities become actual realities, each in its own world. This means that every quantum measurement, every quantum decision point, is constantly spawning new, parallel universes. These worlds don't interact. They are effectively sealed off from one another due to a process called decoherence. So why does it feel like there's only one outcome? Because from our perspective, within any single branch, that's all we can experience. The many worlds interpretation is mathematically elegant, avoiding the tricky measurement problem of other interpretations. While it postulates an almost unimaginable number of coexisting realities and presents challenges for direct testing, it remains a profound and compelling way to understand the deepest nature of quantum mechanics and perhaps reality itself. In the late 1930s, as global tensions mounted, a revolution was brewing in the world of physics. Scientists across Europe were bombarding uranium with neutrons, hoping to create heavier elements. But in 1938, German chemists Otto Hahn and Fritz Strassmann, through meticulous experiments, found something utterly unexpected: lighter elements, like barium, among their reaction products. Confused, they shared their findings with Lise Meitner, their exiled Austrian colleague, and her nephew Otto Frisch. Together, Meitner and Frisch pieced together the stunning truth. The uranium nucleus wasn't just chipping, it was splitting in two, a process Frisch coined nuclear fission. This fission released an enormous amount of energy, and crucially, more neutrons. The implications were profound and terrifying. If these newly released neutrons could split other uranium atoms, a self-sustaining chain reaction was possible, unleashing unimaginable power. News of this discovery spread rapidly, just as World War II ignited. Fearful that Nazi Germany might develop an atomic weapon, Albert Einstein, urged by Leo Szilard, wrote to President Roosevelt. This set in motion the top-secret Manhattan Project, a colossal American-led effort. Under the scientific direction of J. Robert Oppenheimer at Los Alamos, thousands of brilliant minds raced against time, tackling unprecedented scientific and engineering challenges to harness this atomic power. From achieving the first controlled nuclear chain reaction in Chicago, to enriching uranium and producing plutonium on vast industrial scales. Finally, on July 16, 1945, in the New Mexico desert, the Trinity test saw the first atomic bomb detonate, unleashing a power never before witnessed. Less than a month later, atomic bombs were dropped on Hiroshima and Nagasaki, Japan, bringing a devastating end to the war and ushering humanity, with all its hopes and fears, into the nuclear age. The hunt for Planet 9, the unseen giant thought to shape distant solar system orbits, has a fascinating twist. Could it be a tiny, primordial black hole? It's a mind-bending idea. A black hole 5 to 10 times Earth's mass would be merely grapefruit-sized. Directly spotting such a dim, distant object is virtually impossible. But Harvard scientists Avi Loeb and Amir Siraj propose an ingenious detection method. They theorize that if Planet 9 is a black hole, it would occasionally encounter comets from the Oort cloud, the solar system's vast icy reservoir. When a comet gets too close, the black hole's immense gravity would tear it apart. This shredded debris would then accrete, or fall into, the black hole, heating to extreme temperatures and emitting a brilliant, brief flare of radiation. These accretion flares are the key. A regular planet wouldn't cause them, but a black hole would. And the upcoming Vera C. Rubin Observatory, with its legacy survey of space and time, is perfectly designed to detect such fleeting flashes. Scientists predict it could spot one or more flares per year if Planet 9 is indeed a black hole of the right mass. Detecting such flares would be groundbreaking, potentially solving two cosmic mysteries, confirming Planet 9's existence and astonishing nature, and providing the first observational evidence for primordial black holes. The universe always holds more secrets to unveil. Long before his name became synonymous with the atomic bomb, J. Robert Oppenheimer, alongside his student Hartland Snyder, delved into the ultimate fate of massive stars. In the late 1930s, the concept of super-dense neutron stars as supernova remnants was emerging. But Oppenheimer and Snyder asked a crucial question. What happens if a collapsing stellar core is too massive even for neutrons to hold it up? In their groundbreaking 1939 paper on continued gravitational contraction, they used Einstein's general relativity to model this extreme scenario. Their calculations painted a truly astonishing picture. They found that if a star's remnant core exceeded a certain mass, now known as the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 times our Sun's mass, no known physical force could halt its inward crush. Gravity would inevitably win. As the star contracted, Oppenheimer and Snyder showed that space-time around it would warp to an unimaginable degree. From the perspective of a distant observer, the star would appear to shrink, its light growing redder and dimmer, its surface clocks ticking ever slower. Eventually, it would seem to, quote, freeze at a critical boundary, the Schwarzschild radius, effectively vanishing from view. This was the birth of the concept of the event horizon, a point of no return. For an observer falling with the star, however, the collapse would continue unstoppably towards a central point of infinite density, a singularity. Within this event horizon, all paths in spacetime led inward. Escape, even for light, becomes physically impossible. Though initially met with some skepticism and overshadowed by the looming war, Oppenheimer and Snyder's paper laid the mathematical foundation for our understanding of black holes. It was the first rigorous, theoretical description of how such objects could form from stellar death. Decades later, as new astronomical discoveries like quasars emerged, their pioneering work was recognized as a cornerstone of black hole physics, forever linking Oppenheimer's name not just to earthly fire, but to the ultimate gravitational abyss. The cosmic giant we now know as TON 618 began its journey into our understanding as an unassuming faint blue dot. Catalogued in 1957 by the Tonantzintla Observatory in Mexico, it was initially dismissed as just another distant star in our galaxy. But the 1960s and 70s brought the dawn of quasar science. Astronomers were discovering incredibly bright, distant objects powered by unseen forces. The true game-changer for TON 618 came with spectroscopy. When its light was analyzed, it revealed an immense redshift, meaning the light had traveled for billions of years, stretched by the expansion of the universe. This wasn't a nearby star at all. This colossal distance meant TON 618 had to be intrinsically, unbelievably luminous, far brighter than any single star or even entire galaxy. The broad emission lines in its spectrum were the telltale signature of a quasar, a supermassive black hole at the heart of a distant galaxy, furiously accreting matter and blazing across the cosmos. While its quasar nature was confirmed in the 1970s, the full, mind-boggling scale of its central engine came into focus later. Further observations and refined calculations revealed that TON 618 is powered by one of the most ultramassive black holes ever detected, weighing in at an astonishing 66 billion times the mass of our Sun. From a speck on a photographic plate to one of the most extreme objects known, TON 618's story is a testament to how our view of the universe can be transformed by new tools and deeper understanding. The double-slit experiment, a cornerstone of quantum physics, brilliantly reveals the deeply strange nature of reality at its most fundamental level. First, picture firing tiny marbles, one by one, at a barrier with two narrow slits. Behind this barrier, a screen displays where they land. As you'd expect, two distinct bands appear, corresponding to the marbles passing through one slit or the other. Straightforward. Now, consider waves, like water waves, encountering those same two slits. The waves emerging from each slit spread out and interfere with each other. Where wave crests meet, they amplify. Where a crest meets a trough, they cancel. The result on the screen is an interference pattern, a series of alternating high and low intensity bands. This is classic wave behavior. Here's where the quantum world truly bends our minds. Let's fire particles like electrons, one at a time, so they can't interact with each other. Astonishingly, even when fired individually, these electrons gradually build up that same wave-like interference pattern on the detector screen. It's as if each single electron somehow explores both paths simultaneously as a wave, interferes with itself, and then registers its arrival as a single point. But the enigma deepens. If scientists decide to peek and place a detector by the slits to determine which slit each electron actually passes through, the quantum magic shifts. The very moment we gain knowledge of the electron's path, the interference pattern vanishes completely. The electrons then behave just like our simple marbles, forming only two distinct bands on the screen. The act of observation, of measurement, fundamentally alters the outcome. It's as if the electron knows it's being watched and chooses to behave as a definite particle rather than a spread-out wave. The double-slit experiment unveils the core mystery of wave-particle duality, the extraordinary ability of quantum objects to exhibit both wave-like and particle-like properties, depending entirely on how, or even if, they are measured. It powerfully demonstrates that in the quantum realm, the observer is not merely a passive spectator, but an intrinsic part of the system, challenging our deepest intuitions about reality. Imagine trying to photograph a ghost, something that, by its very nature, devours light. This was the colossal challenge facing astronomers wanting to glimpse Sagittarius A star, the supermassive black hole, a 4 million solar mass behemoth lurking silently at the fiery heart of our Milky Way galaxy, 27,000 light-years away. To see it would require a telescope with vision so sharp, it's like trying to spot a single grain of sand on the beaches of Los Angeles, all the way from New York City. No single lens on Earth could ever achieve this. So humanity built a virtual eye the size of our planet, the Event Horizon Telescope, or EHT. This isn't one instrument, but a symphony of radio telescopes scattered across the globe, from volcanic peaks in Hawaii to the desolate plains of Chile, from Spanish mountains to the frozen Antarctic plateau. Using a breathtaking technique called very long baseline interferometry, these distant eyes are precisely synchronized by atomic clocks, observing Sagittarius A star in unison. They become facets of one colossal planet-spanning lens. What they capture isn't a snapshot of the black hole itself that remains forever cloaked. Instead, they trace the dance of light and superheated gas caught in its inescapable gravitational grip. We see the black hole's shadow, an abyss of darkness where light makes its final plunge, dramatically silhouetted against the swirling, incandescent glow of matter accelerated to near light speed, a final scream before oblivion. Einstein's theories predicted this gravitational light bending perfectly. Petabytes of raw data, too vast for the internet, are recorded on hard drives and physically flown to supercomputing centers. There, for months, intricate algorithms, as ingenious as the telescopes themselves, painstakingly weave together these faint cosmic whispers, correcting for Earth's turbulent atmosphere and instrumental quirks to reconstruct one astonishing image. What emerged was not just a picture, but a profound revelation, direct visual proof of the monstrous yet invisible engine at our galaxy's core, a triumph of global collaboration, relentless ingenuity, and our unyielding quest to see the unseen.